Now we would like to write mesh current equations. Let's say another way around. We would like to introduce you an example for a mesh current method analysis. So we've got a circuit here, and it has got 3 meshes. So the first step is to write the Kirchhoff voltage law equations for these meshes. The second step is transfer all voltages to currents by using the definition relations if possible. If not, leave the variable as it is, and then transfer all the elements currents to the mesh currents and find it out, and write supplementary equations if required. So we've got to start to write the Kirchhoff voltage law equations, independent ones. So how many equations do we have? And let's make it black color or black color. Let's create that. And E minus ND plus 1 is equal to 3, isn't it? So we are going to write 3 Kirchhoff voltage law equations. First step. And then what we do next, definition relation. Translations. Transfer the voltages to element currents, and then element currents then mesh currents. These are the steps. That's step 1. Let's make it. That's step 2. And that's step 3. Meanwhile, there are some exceptions that we would see that when you say definition relations to element currents, maybe we cannot apply this. In this case, what we are going to do, we're going to explain it later on. So once again, that we have done it already, and we're going to repeat it once more. When the circuit is given to you, all the dependent sources references are given. The other element references are not given. Therefore, we've got to choose element references for non-source elements. So for the resistors, that means. So we could choose this one, for example, like that size. That way, this has already been chosen. Choose this one as this way, and this one this way, and let's say this one is this way. So according to passive sign convention, this direction of this element current is going to be that way, and for this one it's going to be that way, isn't it? So we have chosen all the current references for all the elements here. So we said we're going to write Kirchhoff voltage law equations. In order to write these equations, we've got to choose direction for the loops. So let's do this by choosing a different color. Make that this one. So this is mesh 1, and mesh current is IC1, let's say, and the second one IC2, that's the second mesh current, and this one IC3, third mesh current. Now what we are saying here, but choosing the direction, otherwise we can't write the equation we said. So you could choose the direction as you like, no problem, because if you choose other way around, that means you're going to find -1 multiplied equation. Mathematically it is the same equation. So let's start with writing these equations now. The first one, our two elements current reference is the opposite to this element current, so it's going to be minus VR2, and this element voltage is VB and directions are the same, that's why it is going to be plus, and this element direction and the loop current direction is the same, so it's going to be plus VE is equal to 0. And then second one, those two directions are the same. So with second one, we are going to write for this loops, for this and this directions are opposite to each other, so it's going to be minus VE, let's say. And then this element voltage. What is this element? So let's take this, let's examine this. Maybe different color would be better. So this element, dependent source. Why it is dependent source? Diamond shape. It is dependent current source. So we're going to say, add more here, dependent source, current source, dependent current source. Why it is dependent current source? Because current reference is given. So, and this current depends on another current, which is this current. So if you're going to write the definition relation of this one, it's going to be like that. I current controlled current source current is equal alpha times IB. What about the voltage of this element? It is this V current controlled current source voltage. It is unknown. That's the definition relation. Okay. So you've got to pay attention to this. So we are going to write the voltage of this. So the voltage of this is this, isn't it? You don't write alpha IB. If you write so, you're in trouble. Why is that? Alpha IB is the current. You are writing the Kirchhoff voltage law equation. You cannot write the current. So you're going to write this one. So what about the sign of it? This direction and this direction opposite to each other was going to be minus, make it black, minus V current controlled current source voltage, plus VC, because of that same direction it is going to be plus, and VC. VB and VC here, since they are independent voltage sources, these are the knowns, isn't it? Mathematically, these are going to be on the right hand side of this equation. So, and this one, the third one, is direction the same, isn't it? So, plus VR1, and this is opposite, that direction and this direction opposite, minus VC, and this same direction, so plus V current controlled current source voltage, and minus VB is equal to 0. Why it is minus? Because this, we are writing this mesh current, Kirchhoff voltage law equation for this mesh, so that direction and direction is opposite to each other. I'm not writing the VL's Kirchhoff voltage law equation for this mesh. For this mesh, that's why it's going to be minus. So we finished that. That's the first step. So second step, maybe you can write it just underneath here. Definition relation R2 times ER2 plus VB, stay as it is, and this is RE element, RE times IE. So we are writing the definition relations of the resistors, no problem, equal to 0, and same as minus RE IE. Now we cannot use the definition relation of this. Why is that? If you look at here, definition relation is this, isn't it? I cannot use that definition relations because I don't know what VCCES is. We know this, but in the definition relation we do not have the voltage of this element. So we are going to keep it as it is. That is going to be the reason that we need to write a supplementary equation. Why is that? Because our expected unknowns here in this method is the mesh currents. So I cannot transfer this variable to mesh currents because I cannot transfer this voltage to a current. That means I cannot transfer it to mesh currents. So that means I cannot get rid of from this variable. That means a new unknown came in. Since a new unknown came in, I've got to write an additional supplementary equation. How I'm going to write it, I will do it at the end. So keep it as it is, minus VCCCS. VC is this resistor, isn't it? Plus RC, IC, and VC, that is independent voltage source. We are going to leave it as this. This is known, isn't it? This is known, and this VB is also known. So for R1 plus R1 ER1 VC minus RC EC plus VCCCS minus VB equal to 0. So that's the second step. Third step is replace all these elements. This is the third step. Replace element currents to the mesh currents. So we are going to replace these element currents to mesh currents. So let's do it now here in this area. RE R2. R2 current is this, isn't it? ER2 is this. So there is only mesh current passing through this element and the direction is the opposite, so it's going to be minus IC1 plus VB RE times IE. Now this current has got two meshes passing through this element, so direction of the IC1 is the same as the element current reference, so it's going to be plus, and this one is the opposite, so it's going to be minus. So that means IC1 minus IC2 equal to 0. And this one, same as this, or the in front of it is going to be minus, so minus RE IC1 minus IC2. We cannot change this, so we're going to keep it as it is, minus CCCS plus RC. So RC is this resistor. So there are two mesh currents passing through this element. So IC3 direction is the opposite to this one. So it's going to be minus, and this is the same direction. So IC2 minus IC3. IC2 minus IC3 is equal that RC plus VC equal to 0. So the last one is R1. Directions are the same. IC3 and the R1 current directions are the same, so it's going to be only one mesh current we've got here, so only the IC3 is equal to that current, and minus RC. RC current is IC2 minus IC3. Plus V current controlled current source voltage minus VB is equal to 0. Now if you look at these equations now here, we've got IC1, IC2, IC3 unknowns plus this VCCS. So unknowns IC1, IC2, IC3 and V current controlled current source voltage. So I've got three equations, four unknowns. I've got to write the additional equation, which is called supplementary equation. How I am going to write it? This new variable introduced because of that dependent source. So I couldn't use this dependent source definition relation while we are writing these equations. So I will be using this element definition relation, which is already written here. So this is the origin of this, our definition relation, which we are going to end up with the supplementary equation. If you write this in this form, this is not the supplementary equation. We've got to transfer all the variables in this equation, in this definition relation, to the variables that I am looking for. That means IC1, IC2, IC3, or if needed, VCCCS. So how I'm going to do it? It is easy. I know that all the elements currents can be written in terms of mesh currents. So I am going to write that ICCS current in terms of mesh current. So this is this element. This element current is this, and this element belongs to different meshes. So this element current is equal, since the direction is opposite to this one, this is minus C2, so direction of this one is the same as the element current reference, so same, so plus IC3 minus IC2. IC3 minus IC2. We are saying that is this. And then is this equal alpha times IB. IB is this current. This current also belongs to two different meshes, isn't it? So IB direction is the same at IC1, but opposite to the IC3. So IC1 minus IC3. So IC3 direction is the opposite my element current reference. IC1 direction is the same direction, so it is IC1 plus, the other one negative, and make it now a bit different color. How I wrote this is what I wrote here, is that IB here. So this equation here, let's make it different color once more. The last one. Now this is supplementary equation. Supplementary equation. So we could say that now here these are the unknowns. So in here in these three equations I wrote the fourth equation. So altogether I've got 4 equations and 4 unknowns. So I can find out all the elements, current and voltages. That is the next step. I mean, I can find all these unknowns here. That means mesh currents plus the current controlled current source voltage. I can calculate that. So you could easily say that if you know what the IC3, IC2 is, then you can calculate VCCCS, isn't it here? So what we are seeing after this, once we found all the mesh currents, we can find this resistor current, we can find this element current, which is equal IC1 minus IC3. We can find this element current, IC1 minus IC2. I can find this element current, IC2 minus IC3. This element current is equal to IC2. And this element current is IC3. So I found all the elements currents. If you use the definition relations, you can find the voltages of these elements. So R1, RC, RE, resistors. This element voltage, I already found it from these equations. This element voltage is known, it is independent voltage source. This element also is an independent source, voltage is known. So that means after that, I can easily find out all the elements, current and voltages. This is the analysis. So we have done the analysis as well. The last thing that we could see about this method, so we have done step by step here. We have used 3 steps in order to get that result. But you can directly write this equation, these 4 equations. How are you going to write it? You've got to know that. You've got to start from the Kirchhoff voltage law equations. So that means you can write that is. So we made a mistake, isn't it? So that minus has been forgotten here. So that's going to be minus here, and that's going to be minus. So what is this is same as this. So consider that you are writing minus VR2. As soon as it is, when you see it for this element, you can write the definition relation. You can write directly definition relation, and then in that definition relation, you can replace the current with the mesh current. So you can directly write this. Maybe I will do it somewhere else. Let me take this a bit this way, okay, and write this here. Now I'm going to write these 4 equations directly by looking at this circuit. So I'm writing Kirchhoff voltage law equation. So writing from the R2. So I said minus R2 element definition relation, R2 times ER2. ER2 is minus IC1. I wrote this is the voltage of this R2 resistor. And then plus VB, which is known, independent voltage source voltage, plus this direction of this is the same as this mesh current. So plus RE times ERE. I'm not going to write ERE. I'm going to write ERE in terms of mesh currents. So there are two meshes related to this one, to make an open parenthesis. And this first mesh current direction is the same of this element direction, current reference direction. So it's going to be plus IC1 minus IC2. Why it is minus? Because direction of this element and this mesh current is opposite to each other, so I put minus there. So equal to 0. Don't forget that you got three terms here and you got three elements in the first mesh. So I have checked it at the same time. So the second one now. So in this mesh I've got four elements, so there's going to be four terms here. So this first one is going to be the same as this one, isn't it? Only the difference is going to be for the first mesh, the sign of VRE is positive. In the second one, since these are opposite to each other, it's going to be minus. So minus RE EC1 minus EC2. And then this element voltage, directions are opposite, so minus V current controlled current source. And this element direction reference and this reference the same, so plus RC times, I am using the definition relation at the same time, this element current in terms of mesh currents, there are two meshes related to this one. IC2 direction is the same as the element current, so that's plus, and the other one is the opposite, IC3. And this element direction the same as this one, so it's going to be plus VC. This is independent voltage source voltage, which is known. So I wrote the second mesh Kirchhoff voltage law equation, use the definition relation of the resistors, and use at the same time element resistor element currents in terms of mesh currents. This is what I have done. So the last one has got four elements once again. So this one, for example, minus VB. And that R1 direction is the same as IC3 direction. So the sign is going to be plus R1 times R1 currents in terms of mesh currents equal IC3. So RC, what I wrote here, it's going to be the minus sign here, isn't it? For this mesh, it is going to be plus. For the other one, it's minus. So I'm going to write minus R2 IC2 minus IC3. And plus VCCCS equal to 0. So I wrote this third mesh Kirchhoff voltage law equation here. Since we introduce a new variable here, we are going to write supplementary equation. How we are going to write it, as I explained here. So if you put this one as well, that means you wrote mesh current equations for this circuit directly. So that makes it easier. If you are doing it at the beginning, you could do it step by step. Once you get used to it, so you can directly write mesh current equations for the related circuit. So don't forget, first of all, what is the use of this method? We've got to explain that. If we didn't use this mesh current analysis method, we were going to 1, 2, 3, 4, 5, 6, 7 elements we've got here. We were going to solve 14 equations. So how many equations that we are going to use here is just 4. So that means this has got 10 additional equations. So just only 4 equations that we are going to solve. That's why that method is better than the classical 2-any analysis. to any equation analysis, classical method analysis. It's better than this because it is just 4. So don't forget, although we are going to solve these 4 equations here, after that what we found is not all the elements current and voltages. We are going to find all the elements current and voltages by using these mesh currents, but that is very easy, a simple relation, so you can directly write them down as I explained already. So that is the end of this video then. Close it. Close it. Get this one.